I was reading something recently about technosignatures.
Yes.
Um, and I kind of want to lead this into the James Webb stuff, but and I know I didn't prep you about this in
Yeah.
advance, but it's just off the cuff, just curious, like how they're using. Matt, you know the process.
Yeah.
How do they check for technosignatures?
Okay. First things first, they check using a technique we call spectroscopy.
Mm-hmm.
Okay. And so I'm going to start off with a lecture, a brief lecture. I say brief; it may turn into a lengthy one
It's fine.
about spectroscopy. So I'm going to ask you to bring up Figure 1 because what is spectroscopy? And spectroscopy is we break apart the light that comes from an object,
Oops.
and we look at the colors. And so the first thing we look at is these plots right here, because something that has a temperature greater than 0 Kelvin will give off light in this type of pattern. Okay, these types of curves. So if you notice, there's a peak to the curve, a highest point, a highest intensity. So one of the first things we do when we break up that spectra is look for where that peak is, that highest point, that brightest point. Because there's a nice little theory called Steph, or a law actually, which we don't want. We don't have a good theory for it yet, but it's called the Stefan-Boltzmann law, and it relates directly where that peak, that highest brightness, that highest intensity is to the temperature.
Mm-hmm.
So the one you've got the cursor circling, that peak is related to 7,500 Kelvin. To put Kelvin in perspective, ice or water freezes at 273 Kelvin.
Mm.
So 7,500 is quite bright.
Yeah.
Okay.
And this is
And if
the
you notice,
what is that? The violet? Is that violet the
that's
color?
violet. Yes.
Okay.
So right away, just looking at which color of light is that highest, that brightest point, tells us the temperature of the object.
Mm-hmm.
So that's the first thing spectroscopy tells us. Then if you'll go to slide 2, it turns out that every element and every molecule out there will absorb light, specific colors, kind of like a fingerprint, except it's more exact than a fingerprint. And so, like hydrogen will absorb light at where you see those dark bands in the rainbow. Okay. So you've got a couple in the violet and blue, deep blue, and then you've got one in the cyan, and then you've got a couple over here in the red, and that's hydrogen. And it's better than a fingerprint at identifying that hydrogen is there. And all of the elements, all of the molecules have these types of absorption lines, we call them. Okay. These are also emission lines. They emit at those colors as well.
Mm-hmm.
But generally speaking, in astronomy, we're dealing more with absorption than emission. Okay. And what happens is because things have a temperature, they shine in that curve that we just saw. And then the light that passes through a material, okay, so that's the temperature. If it has a temperature, it's going to shine like that.
Mm-hmm.
And then if it shines through something, those absorption lines happen. And we're able to tell what that material is made out of.
Okay.
Okay. So I will say let's go to slide 3. And you can start seeing that actually what we see is a little messier than bright and dark lines. Okay. And so that top one is showing you pretty much a perfect spectrum of hydrogen.
Okay.
That we would be looking at from a star. Okay. The lower one actually comes real close to what we actually see. And so you've got all these absorption features, plus noise, plus this other stuff. And so computers have been a godsend because computers can identify where there's absorption lines and match them up to hydrogen or helium or oxygen. Okay. We used to have to do that by eye. And I think you can imagine the nightmare that looking at that lower red line or graph, what a nightmare that would be.
Yeah, it looks like it just kind of trails off, right? You got all this and then all of a sudden,
Yeah. And that's what it does. So you asked about technosignatures. I wanted to go through the basics of what we mean and what we're talking about. So you asked about technosignatures. So what we're looking for is molecules that here on Earth, at least, we've never identified a natural process that creates them. So something that we're talking about would be, what was the one that they went nuts about? And I can't remember its name. But there's a lot of fluorocarbons that are only produced, as far as we know, by factory processes. So if we see fluorocarbons in an atmosphere of an exoplanet, and how we can see that is we take the spectra of the star it's going around, and then we let the planet go between us and the star, and we subtract out what we know the star to be, and anything left over has to be the atmosphere of the planet, right? Does that make sense? Okay.
yes.
Then I'm explaining it well.
I don't know. I'm kind of a turn up, so but yeah, I mean, because like it's not it's because like people like at SETI and all these other observers of space signals are looking for. They were looking for these direct signals, like, "Hey, we're ET, yes. We're here," when really they should have been looking for, "Hey, I'm ET talking to another ET on this other planet. What's going on, buddy?" Right. Oh, look, we're making all this stuff that nature doesn't make. That sort of. So that's what you're looking for, right?
Right. Well, we're looking for the lines in those spectra that we were just talking about that say there's this factory pollutant signal in the spectrum.
Right.
Okay. Now, the thing is just because we don't know of a natural process that produces that molecule does not mean there isn't one. So finding one, as we call it, technosignature, is not going to be an indicator that, hey, there's factories blowing shit into the air. Oops, sorry.
Well, they might be throwing shit in the air. You never know.
Yeah. So we one will not do it. People will go, yeah, this is a good indicator, but there may be some natural process we haven't found yet that produces it.
Right.
You start getting 2, 3, 4. Again, we're back to you're now stretching that rubber band of credulity to the point of it breaking. That's not natural. That's not normal. That's somebody running a factory.
Yeah.
And so that's kind of what we're looking for. And again, how we determine it is the star has a spectra like we just showed. Okay. The planet goes in front of us, between us and the star. Well, the star's light is shining through that atmosphere. And as such, it's absorbing some of those colors, those wavelengths. So we subtract out the star. Anything left over must be that atmosphere. Yeah. And so that's what we're looking for.
It's almost like Occam's razor, right? You just kind of have to eliminate all the others till you get to the one that makes the most sense.
Kind of, sort of, yes.
Well, I'm no scientist. That's how I do it as a non-scientist.
We do a little of that,
But you do it in a more, precise, measured way, of course. Yeah.
Right. The subtraction is usually done because I know this. For instance, sunlight traveling to us here on Earth's surface goes through our atmosphere. And so we subtract out the atmospheric lines. We call them the telluric lines. We even have a name for it. Okay. And so we know they're there, so we'll subtract them out. Okay. So when we know something is there, we'll subtract it out. Now, we then do make the assumption that everything left over must be the planet's atmosphere. How good an assumption is that? Probably pretty good. And that's what we base things on. Okay. Could it be that we're getting some other signal? Absolutely. It could be there.
Yeah.
But for right now, nothing suggests that it is. So that's what I have to tell people, they go, oh, see, science proved itself wrong. It didn't prove itself wrong. It proved itself better. We found out something that refined it down oh, we weren't taking this into account. That change doesn't change things. What it does is it narrows down the possibilities. And, again, we like that.